Okay, so let's look at recitation problem number 4. In this problem, we're given a language, MTDFA, which is the language of all DFAs encoding in which their language is empty. And what we want to do is to use the decider for the MTDFA to basically decide no odd and inf DFA. So what we want to do is to use the decider TM, and here we denote it as empty DFA as a subroutine to decide no odd and inf DFA. So we start with no odd, and one intuition is we want to somehow connect this language to empty. And let's look at the definition of no odd. No odd is contains all the encoding for DFAs in which the language does not contain any string that has an odd number of ones. So basically, like intuitively, we can just like consider that the language no odd, or like a DFA, a D inside no odd, and we know that the language of D and intersect with odd is going to be empty, where odd is the language that accepts all strings with odd number of ones. Okay, and you should be convinced that this language here is regular. In other words, we have a DFA that can decide it. So let me quickly draw the DFA for this language. Basically, we accept the first one and bring us to the accepting stage, and more ones will bring us back. And adding zeros does not affect our result. Okay, so this is the DFA for odd. Let's call it the odd. So basically what we want to do is to create for any input DFA into our M, decider M for this language. We want to basically intersect it with our language odd and check if it's empty, which can then like be checked by our empty DFA. So let's define our M here. M takes in an encoding of the DFA, and then we construct D prime such that the language of D prime is the intersection of the language of D and the odd. So then we return an empty DFA D prime. This should be like the correctness of this algorithm is pretty obvious because like if D is inside the language no odd, then we know that our D prime is empty, so empty DFA is going to accept. And on the other hand, if D prime is not in the language, then we know that if D is not in the language, then our D prime is not going to be empty. So and empty DFA is going to reject. So I encourage you guys to check out the recitation solution. How do we like formally write this whole like proof of correctness down? So then let us look at the second part of the question, inf DFA. So inf DFA is like takes in encodings of DFAs in which like the language of the DFA is infinite. So like to solve this question, again, we want to kind of like associate it with with empty DFA. So the way we do it is like we want to gain some intuition of like how DFA actually works, because like we know that any DFA has finitely many states. So if we wanted to accept infinite many strings, then there has to be some loop in the middle, or like in the beginning or at the end of the DFA. So let us prove a lemma that basically formally summarize what we just like mentioned here about the cycle thing. So the lemma is if a DFA with k states accept some string except w such that w is greater than k, then the language of this DFA is going to be infinite. In other words, D accept infinite many strings. So the proof of this lemma is pretty simple. So so basically, like, assume we have a DFA D and it has k states, which our set of states, the cardinality of our set of states is equal to k. And now we assume that it accepts W, which is the can be decomposed into W1, W2 up to Wn, and n equal to k. So this is our assumption. And then, like, we know by pigeonhole principle, so this proof is quite similar to the irregularity proof, like as we did last week. So by pigeonhole principle, we know that there exists I and j such that I not equal to j, and without loss of generality, we assume I less than j, such that W1 up to Wi and W1 up to Wj ends up in the same state. So we call this state Q, and it's inside our set of state Q. And then, like, we know that, so if this is our Q0 and we start at we start at, we start as empty string and we go one by one. So we read W1, W2, and here is our Q, which is a state that's Wi ends up into, and then we read Wi plus 1, I plus 2 up until Wj. And according to our assumption, or like the result of pigeonhole principle, we know that Wj ends up in the same state Q. So this is basically what our like trace looks like, and after Wj, it's going to like maybe leave the loop or maybe not. It depends. But like one observation here is that no matter how many times we go through this loop, so like in other words, we can append Wi plus 1 up until Wj infinite many number of times in the middle of this string, and it will still end up in the same state Q. So put it more formally, we know that Wi up to W1 up to Wi and Wi plus 1 up to, followed by Wi plus 1 up to Wj to the power of n, all ends up in Q for all n in the natural numbers. So this is just like what I just described in this graph. So from that, we can conclude that all the strings of this form, Wj plus 1, Wn, is accepted by D. So this concludes our proof that our DFAD is going to accept infinite many of the strings. So like, remember our goal is to basically set up a connection between inf DFA and empty DFA. So with this lemma, the way we do it is, again, we want to make sure that the input DFA-D and some other DFA, if we either like intersect or do set minus or concat or anything else, will end up in which like in a DFA that accept nothing. So basically the language of the resulting DFA should be the empty set. So it happens to be in this case that we want to do intersection as well. And the language that we want to intersecting with is like made really clear by this lemma. So I'll write it in another color. So if we basically refer a language, what should I call it? So let's call it D prime. Okay. So LD prime only accepts strings that of length greater than k. So you should be convinced that this language is regular and we have a corresponding DFA-D prime that can decide it. And from here, sorry, my notes is getting a little bit messy here, but from here we know that if we do an intersection of an arbitrary DFA with D prime, or just to be like consistent with all the types, we intersect their language. So we know that if it's empty, then this means our language L contains no strings of length greater than k. And by our lemma, we know that this means that our language L is does not accept infinite many of the strings, and vice versa. So let's put it more formally by writing down the algorithm for the decider for inf DFA. So basically the input is a DFA, the encoding of the DFA, and let k be the number of states of D. And then we construct a DFA D prime such that L D prime is all the strings with length greater than k. And then like just as the previous one, we construct a DFA D prime prime such that the language of D prime prime is equal to LD plus LD prime. And here we run our empty DFA on D prime prime. But one thing to know here is that if this DFA accepts, what we should do. In this case, it turns out that we should reject. So why this is the case? It's because like, notice that if empty DFA of D prime prime accept, this means the language of D prime prime is equal to the empty set. In other words, this should be intersection. The intersection of LD and LD prime is empty. And by our lemma, we know that LD is not infinite. It does not belong to the language inf DFA. So that's why we have to flip our result state. So similarly, if reject, we accept. So let's do a simple proof of correctness here. So there are two cases because like to prove the correctness, we need to argue that no matter what the input is, our M is going to like give the correct answer. So there are two cases. The first one is that our input D is inside of the language. Then we know that LD is infinite. And because we know there are like finitely many strings of length, like from 0 to k, we know that D has to accept strings with length greater than k. This means that the language of D intersect with the language of D prime is not does not equal to the empty set. And in other words, empty DFA rejects. And because we flip our accept and rejecting state at the very end, we know that our M accept is expected. So this case is good. And the second case is where D is not in the language in DFA. So in this case, LD is finite. And by our lemma, the contrapositive of our lemma, we know that LD doesn't accept any string of length greater than k. In other words, LD intersect with LD prime is going to give us the empty set, and empty DFA is going to accept, and our M is going to reject. So this proves the correctness of our algorithm or our decider for DFA. So last thing to note here is that actually at the beginning of both of these two algorithms, we're implicitly checking whether like the input to the Turing machine is of the correct type. And this is not like always written down, but it's just like implicitly there. And we can assume that if it type checks, then we proceed in our algorithm. And if not, we just like simply reject.